I'll start recording. Nice to see everybody. So let's see here. In terms of course stuff, hopefully you all finished your homework. It was due yesterday, I think. Somebody already sent me a note asking when you're going to see the next homework, which I'm puzzled by because it's the same cadence as all the others, but I will post it when I get around to posting it. I like to triple check to make sure I don't send you the solutions for the nth time. But yeah, so basically your fifth and final homework will come out sometime in the coming day or two, and then it will be due, 2 weeks after the last deadline, just like always. And that'll be the last homework for this course. So again, remember this class is 5 homeworks and a project. Hopefully you've all completed your projects and are busy drafting your beautiful write-ups by now. I see good furrow eyebrow head shake there, so I'm glad to hear. I'm looking forward to learning all about whatever topology problem you guys ended up solving. And that's basically it for your deliverables for this course. I guess you probably already noticed that Thea posted some grades for some of your assignments, which is good, and that's about it. This is a pretty straightforward course. Any questions organizationally speaking? Bureaucratically speaking? Something? Okay, fantastic. In that case, we're going to continue today in our discussion of Laplace operators. Shocking, I know. And hopefully kind of wrap it up a bit. And then in our next lecture, we'll start on the next topic, which is vector fields. And we'll go from there. I believe this will set our course relative to the schedule online back a little bit, but that's fine. It's my schedule. I made it. I can do that. So today, so rather than diving into vector fields today, I thought we would just wrap up Laplacian. If we're done early, which I always say and then never actually manage to accomplish, then we'll call it because it's hot in this room and like enough already. Sound good? Cool. Okay, so let's see here. So far, what have we done? Well, we have spent basically 3 or 4 lectures just defining this object, right, this Laplacian operator, and talking a little bit about how it can be discretized and used computationally, right? And so far we've seen that in 2 contexts, right? We first saw it defined on a graph, kind of an analogy to what it means to define a Laplacian on a smooth domain. And then in a second case, we spent an entire lecture deriving a finite element Laplacian operator, which you can use on triangle meshes. You also can do this on tetrahedral meshes. You just have to look up the formula for the right kind of analog of that cotan object. And in fact, for all kinds of different finite elements, you choose your favorite basis, do a bunch of nasty integrals, and what comes out is a way to solve Laplace equation, which is what everybody wants to do. Today, we're going to focus on high-dimensional application. So here, our geometry is going to be some manifold which is embedded in a high-dimensional space and is itself a high-dimensional object. And so this is the typical setting that shows up in machine learning world, right? So oftentimes in machine learning, people talk about their data forming a manifold. They throw around that term willy-nilly. Sometimes they mean it for real. Sometimes they mean it for fun. But essentially, the sort of philosophy that I think is captured by these folks, even if the mathematical rigor isn't there, is that like your data set is like cutting out this very thin slice of the high-dimensional space, and that somehow a reasonable way of thinking about it, even if it's not 100% accurate, is that maybe your data is like cutting out some kind of manifold structure in that space, and that you can leverage that structure to do inference, right? So the typical example people talk about is images. Let's say that I have, the space of all 1024 by 768 photographs. If I were good at powers of 2, I could tell you the dimension of that as a space, but it's 2 to the very large number, right? Like basically 1 value per pixel of your image. But obviously, if you just draw a random point in that space, which is like a random number per pixel, are you likely to get a photo of a cat? Well, no. You're likely to get a photo of like, what's that horror movie with the lady that crawls out of the TV and it's got the static? The Ring, yeah, that's right. Basically, you're just likely to get white noise, is what I'm trying to say. And so the reality is that like somehow your embedding space, right, the space of all possible colors assigned to all possible pixels in a photograph is not really representative of your data space, which is probably some very thin slice inside of there, right? And of course, in statistics and machine learning, God, it's hot in this room. We learned one very basic technique for trying to leverage that sort of structure, which is principal component analysis, which is totally reasonable so long as your data is flat. But of course, nobody said that that has to be the case, and that's why this sort of manifold learning community is trying to address, right? So earlier on in this course, when we talked about embedding problems, remember we talked about what were some of our embedding techniques? LLE, thank you. What usually goes with LLE? I zoom out, thank you. And on your homework, you play with a few more. Those are some examples of this sort of like manifold structure being imposed on data and leveraging it to design a clever algorithm. So a different thing you might want to do is do spectral calculations on data set. And there's a lot of reasons why you might want to do that. So for instance, let's say that I'm solving some kind of regression problem. Like I'm trying to think of like a true regression problem. It's like remarkably hard to do. I'm taking photographs of bowls of soup and I want to know the fraction of that soup which is tomato. That's a real valued problem. So, you know, I can do that by collecting a big data set of images and some scalar. I can do regression. And of course, I expect that to be some kind of smooth function of the input, maybe. I realize this is a little contrived. How do I measure smoothness? Well, we just spent basically 3 lectures developing a whole theory on how to measure if something is smooth, right? Like in particular, you know, we derived an energy which is related to Laplace operator, which does precisely that, right? Anybody want to remind me what's the name? Dirichlet energy. Thank you. So having access to objects like Laplace operator, and by the way, more broadly, like differential operators in these high-dimensional settings can be useful and can help you kind of translate these tools from differential geometry to this interesting, abstract, but also very noisy space. Okay? So I thought today what we'd do is we'd first spend a minute talking about what does it mean to put a Laplace operator on a data set. Like, that doesn't have the kind of structure that we needed, right? When we derived the cotan Laplacian, we needed like this manifold triangularized object, and we needed triangles, and they had to be connected in a particular fashion, and so on. Like, if you think back to that derivation, we used every corner of that structure to make a reasonable matrix. But if I just give you a big cloud of data collected from some curved blob, there's a reasonable question you might ask, which is, can I still do some calculation that converges to Laplace operator? Now, obviously, the answer here is yes, because otherwise I wouldn't be giving you this lengthy introduction. And the question is precisely how to do it. Yeah? So I thought I would spend a few minutes today deriving one of the more popular formulas for Laplace operators on point clouds. When I say point clouds, by the way, I think oftentimes we think about it in computer vision context, like point cloud is a bunch of points on a 3D surface. But just generically speaking, a point cloud is just a bunch of data points in some space or another. We'll talk about how to derive such an object. And we'll see that coding it is even easier than coding the cotan Laplacian. In fact, if you're really lazy on a triangle mesh, you can use these formulas. You'll just get a slightly crappier Laplacian. And then we'll talk about a few applications that have been proposed in machine learning literature. And of course, this discipline being what it is, every week if you open up arXiv, you'll find something new. I mean, people find new ways to rebrand the same old ideas all the time. Okay. Our basic setup makes sense? The motivation, what we're trying to do here? Fantastic. Okay, so let's make some Laplacians on point clouds. I don't have slides for this, so we're going to be on the board. As always, I have terrible handwriting, so you'll have to tell me if you get lost. But I did the old school thing where you like actually read the research paper and then take notes so you can teach it in class. So that's what we're going to do. Okay, so our goal here is to derive a point cloud Laplace operator, and just like that. So, and in particular, we're going to derive one of the very first ones that was proposed in the literature. And what we'll see, actually, if you dig through more modern literatures, they're all basically the same up to rescaling. Like, of course, it's easy for me to say that there's like all kinds of intimate details in how you choose that rescaling and so on. But at least, like, yeah, kind of spiritually, these operators tend to follow a similar form to one another. Okay. So in particular, the one that we're going to derive is from Belkin and Nyogi. This is one of the more famous research papers in this discipline. Incidentally, Misha Belkin is like just this fantastic speaker, and if you ever get a chance to see a talk from him, you should, because he's like one of these people. You know, I feel like there's occasionally a researcher that'll like come through MIT and they'll give a talk on some totally obscure math topic that nobody should care about, and I'll just be like ready to like march on their orders and do precisely the research program they want because it's just so cool and smart the way they talk. And he's one of these people. So anyway, you should look him up and watch him give a lecture because it's much better than the garbage you're seeing here. Okay, so here's our input. We're given some kind of point cloud. You can tell it's a point cloud because I did that scrapey board thing. And notice I've drawn this in a very suggestive fashion, which is that we've got a bunch of points here, and these are all sampled from some low-dimensional manifold, right? Like in this case, it kind of looks like a curve, right? Now, unfortunately, it's obviously, there are different ways to make Laplace operators. One thing I could try to do would be to reconstruct the topology of this object. So in other words, to connect these points together into a curve, and then use like what we did in the last couple lectures. But of course, that's a messy procedure, right? And especially when these points get noisy, that becomes something that is very unlikely to succeed. Moreover, that's maybe okay for triangle meshes, but like if you have like an 8-dimensional manifold, then like the number of 8-dimensional simplices you'll need to construct will exponentiate. That gets to be a messy process. Okay, so essentially our input here is some data set xi, which is, I don't know, what dimension do we want it to be in? How about Rn? Sampled from, and then we're going to say that it's a manifold, cursive m, and maybe even give it the little subscript, little m, which is the dimension. So like, for instance, for this guy, n would be, what would be the dimension that the point cloud lives in? 2. Thank you. I only asked like the same 3 questions over and over again. And little m would be 1, right? Because it's a curve. Okay. All right. So first of all, like when we derived Laplacians in our last couple lectures, like we just started like integrating like crazy people. But unfortunately for us, what are we missing? Well, we don't really have a reasonable gradient operator or a reasonable notion of integration unless we define it, right? Like we just have a bunch of points. I mean, maybe integration you could do by just summing over the point cloud. But essentially, all the ingredients that we used to write down our Laplacian before are missing. All we have are a bunch of points. And that's the problem we want to face. So back to the drawing board, which I guess in this scenario is this board. Okay, so what we're going to do, which is kind of funny, is actually flip backward some constructions that we did in the previous lecture. Namely, if we have a Laplacian, we have a heat kernel. If we have a heat kernel, we have a Laplacian, right? So here's what we're going to do. We're going to start from the heat equation and work backward to get a reasonable Laplace operator. And this is like a really clever little trick from Belkin and Niyogi here. And essentially what they do is they're going to write down a formula for the heat kernel that kind of looks like a Taylor series. And then they're going to truncate it and notice that the truncated version of that you can approximate with points without knowing the connectivity. It's a really sneaky little trick here. This is only a first order approximation, meaning that your sample here has to be pretty dense before this thing actually works. And there's a lot of subsequent research that tried to figure out like precisely the convergence rate. Can you be a little bit more robust to noise, that kind of thing. Okay? But we're just doing the basic version. So the equation, which hopefully we now all have memorized and tattooed on our forearms, is the heat equation. That's the one we're going to be studying now. And what is it? It's du dt is equal to minus Laplacian of u. And just as a reminder, again, the Laplacian is only in the spatial variable, right? Not in t. Right? And so what does this thing do? It's given some like initial distribution of heat on our domain. Here, this is a manifold. This tells you, as a function of time, kind of how it spreads out. By the way, the phrase distribution of heat is squishy. I mean, like literally, it can just be temperature at every point. I feel like we try to avoid that because mathematicians are bad at physics. Okay, so there are a lot of different ways to solve the heat equation, I think. And already last time we kind of sketched out, actually we did it for the wave equation, but the heat equation is basically the same. We sketched out one particularly easy way to solve linear PDE using some more stuff that we know about the Laplacian. And if you recall, what did we do? We kind of wrote everything in terms of eigenfunctions of delta here. And then we saw that like life just became much easier in that setting. So let's do exactly that, just as a bit of review. So in particular, let's say that we have an eigenbasis which satisfies that like Laplace of phi k equal to lambda k phi k. Okay? So we have a bunch of eigenvectors of our Laplace operator and they span the space of functions. Okay? So right, what we're going to do is we're going to write our function u of x t, that was a u in case you're wondering. We can write it in this basis. And the way that we do that is we just say, okay, we're going to just say, like at every fixed time, u is a function of the surface, so I can write it in the basis. So the uk will be the coefficient. And my notes have a typo, but what I meant to write was phi k of x, like that. Okay. Hopefully this picture is becoming boring to you by now, if it wasn't before. Incidentally, if you've taken a PDE class in the math department or engineering or whatever, you might recognize this as a thing you do on day one, but they don't really motivate it. They call it separation of variables, right? Where they kind of say like, oh, I have some unknown thing and I'm gonna write it as the product of like one function and one variable and one and the other. I always thought this was like super unmotivated in PDE textbooks. It's like the very first trick that they show you. But the reality is like this is kind of where it comes from. So for linear PDE, it really does make some sense. Okay, so sorry, I got on my soapbox and got distracted. What are we doing? We're solving the heat equation. Right, so so we have du dt equals minus delta u. So if we write it in this basis, what is du dt? Well, I pass the derivative in t to the inside to all the uk's. Right, so I have the sum over k of uk prime of t phi k of x is equal to minus Laplace of u. So minus the sum over k of uk of t. And what is Laplace of phi k? You said it. Now like 3 times louder.
Lambda k phi k.
Lambda k times phi k. Thank you. I can't be the only person that yells in this room. Okay. So we're doing this quickly because I think we've seen this a number of times. Okay? So now we use a quick linear algebra argument, right? We've taken this function u and we've written it in the phi k basis kind of in 2 different ways at every fixed t, right? There's these coefficients and these coefficients. And what do we know about an orthogonal orthonormal basis? Well, we know that this decomposition is unique, right? If I can write a function as like some coefficient times the phi k, that coefficient, there's only one choice. In other words, our basis is not linearly dependent. Or to put it differently, it is linearly independent. Okay, so in other words, we can basically just set the coefficients equal to each other. Yeah? So what do we know? We know then that uk prime is equal to minus lambda k phi k. Nope, just kidding. uk. Right, where these are just functions of t now. There's no x involved. This is an ordinary differential equation. It should look very familiar. Right, this is just exponential decay. So for our final trick, what did we show? We showed that uk as a function of t is really uk at time 0 times e to the minus lambda k t. Cool? Hopefully this story is beginning to look kind of familiar and crank turny. Right, like there's just a few tricks that we just keep using here, right? One is like variational derivatives, another is like write everything into basis and just like turn the crank. Okay. Fantastic. So now we're going to start doing something slightly different. So, but close. So remember in our previous lecture, we defined an object that we called the heat kernel signature. Remember what this thing was? It was like I kind of put a delta of heat at one point and then just measure how much of that heat is left as a function of time. And I think Karthik cleverly pointed out that you also have to normalize this thing because the functions looked like they were increasing and that doesn't make any sense. That's my bad. So here we're going to define an even slightly more general object, which is going to be that I'm going to put a point of heat at x, and then I'm going to like plant my toes at y. And as a function of time, I'm just going to measure how much heat has made it from x to y as a function of time. Okay? And basically from this heat, from this expression here, we very quickly read off by integrating it against delta function that we can define a heat kernel ht of, I guess, x and y here. And any ideas so like what this function should be, if you remember from our discussion of heat kernel signature? So chances are there's like an e to the minus stuff hiding in there somewhere, right? Huh? Possibly, but so I'm gonna think about it this way. So remember, like, what are the u naughts in the case that I said I put in a point. Do you remember how we did this last time? We like put a delta function in, and then what did we get? We got like phi of x, and now we're going to measure it at y. Now, does this sound familiar at all?
Yeah. But if you put a delta function u naught, then once you have it completely distributed, because then you're going to have just one eigenfunction being active.
There's definitely more than one eigenfunction.
Say if only one u naught is non-zero,
Mm-hmm.
u being the coefficients of the Laplacian
Mm-hmm.
eigenfunctions, we will have distributed each.
Absolutely, and that's why more than one is non-zero. Yeah. So let's, if you recall from our last lecture, like let's say that I have initial condition u naught of x like that. Then how did I get u naught k, or like these coefficients? Well, it's just the inner product of, I guess, in this case, phi k of x with u naught x, like that, right? So let's say that I put a pinpoint of heat at x, and then I want to measure it at y, okay? Then, so if I have a delta at x, if I crank through this formula, so I've kind of reused x here, sorry, it's the integrand, but now it's just a special point, then what should u naught k be?
Phi k evaluated at?
That's right, yeah. So u naught k is going to be phi k evaluated at x. Does that make sense, everybody? Fantastic. So now, if we go up here, we can read off our solution to the heat equation. Yeah. And remember that here, yeah, so we have this x and this one, I guess, are different. I'm sorry, I keep reusing the same x. But that's fine. We can like maybe think of, let's make this a y. We'll diffuse from y to x instead of from x to the y, and then we'll notice that that's symmetric. Is that okay if I manage to confuse everybody yet? Because I can keep making mistakes until you do. Okay. So how much gosh darn it. I blame the temperature in the room. How much heat goes from x to y in time t? Well, if we go here, right, then what is our distribution if our initial condition is a delta? Well, let's see. It's the sum over k. Right, like we just write the formula for u right there, right? So sum k, and then what do we have? We have u k of t, which is really u naught k times this decaying exponential, right? So we can say e to the minus lambda k t, and then here u naught k is phi k of y, right? Because that's our initial condition, and now we're measuring it at x. So now this phi k gives us another term like that. Does that make sense? Everybody see where the heat kernel comes from? It's a really tidy little formula. Okay, so that's the heat kernel. I'm going to erase these two lines, if that's okay, so I have a little bit of space. By the way, now we can notice that if I swapped x and y, I get the same formula. So this is a symmetric object. Which I guess a priori didn't have to be true. Like there could be a universe where it's more easy for heat to diffuse from me to you than the other way, but apparently not. Okay. Cool. So this is the broad picture. I'm going to spare you some excruciating pain here and just give you a few formulas. Namely, given this object, you could work out the heat kernel on like Euclidean space easily enough, right? You'd work out like, we're like on a square at least, like some compact domain. Like, so on, for example, on the unit interval, remember that the eigenfunctions of Laplacian are like cosines and sines. So this would give you some infinite sum you'd have to evaluate to get the heat kernel. That make sense? So I'm going to give it to you, because that's no fun. On Rn, where now, by the way, the eigenfunction argument falls apart a little bit because you have more than countably infinite many, but that's something to worry about another time. We have the following formula for the heat kernel at time t. It's equal to 1 over 4 pi t to the n over 2, sorry, I'm just copying this, e to the minus mod x minus y squared divided by 4t. Does this formula look familiar to anybody? We're nodding. Yeah, it's a Gaussian. It's a bell curve in the difference between x and y, right? So essentially, what does this show? This shows that like heat diffusion is the same thing as just like integrating against a bell curve. That's all that's going on in the plane. Moreover, does anybody want to prove to me Varidan's theorem in the plane? Remember what it says? In fact, I don't remember what it says, but I can eyeball it from here. Right? It's, if I take the log of the heat kernel, subtract an appropriate constant, multiply by -1, and take the square root, then I get distance, right?
Multiply by 4t as well?
Yeah, sure. We'll throw 4t in there. Yeah. Essentially, from this formula, it's very clear that distance and heat diffusion are linked together, at least in the plane. That's what I'm trying to say. Okay. So, in this universe, life is good. Like we have a nice heat kernel. It's in closed form. We can do nice stuff. On a manifold, we don't. Like on manifolds, the rate at which heat diffuses has to do with kind of how area locally is changing as I move from point to point, right? Like if I have lots of excess area for every unit of distance, like in a negatively curved region on the surface, then maybe heat can diffuse out more quickly and so on, right? But it turns out that there's a really handy approximation of the heat kernel that gets used quite a bit. It is outside of the scope to prove this formula. And when I say outside, in this case, I mean outside by like a very large margin. But this is the kind of thing that you can find in a textbook easily enough, which, by the way, is what everybody in this research field does. And it says the following, that the heat kernel, oops, that should have been a Y. It can be written as follows. And this is a really handy formula, by the way. I noticed a few of your projects involve these kinds of constructions, and this is a useful kind of rule of thumb to remember, which is as follows. Times. Okay. You know what? I'm going to change notation from Misha Belking a tiny bit, which is a dangerous thing to do. Okay. So here's what it says. It says that the heat kernel on a curved manifold sitting in Rn satisfies the following formula. It looks an awful lot like what we had before, but there's one small difference, which is the coefficient here is m. It's the intrinsic dimension of our manifold, not the extrinsic one. And that kind of makes sense because this coefficient is the thing that wants your function to integrate to 1, right? Like this is kind of like dividing by the integral. And here, if you think about it, the integral is on some lower dimensional object. So it makes sense that m would show up somewhere, right? And it's multiplied by a pair of things. This is, again, kind of like separation of variables, right? I have one thing in space and one thing in time. So this big O notation just says that there's some function that goes to 0 for small t. It's a complicated one. And then this phi satisfies, or psi rather, satisfies one really nice function, or property rather. So for one, psi is smooth. And for the other, psi has a property that psi of x comma x is identically equal to 1. So in other words, like the way that we modulate the heat kernel kind of along the diagonal, like heat diffusing from something to itself, really isn't affected a whole lot by curvature. Okay, so this is like our handy little Taylor formula. It kind of does two things. For one, it says like, well, this looks an awful lot like just heat diffusion in a flat m-dimensional space, right? That's what this piece is saying. But it does have to get modulated by something. But the good news is that the coefficient that modulates it is basically 1, as long as points are close by and time is small. Does that formula spiritually make sense? Yes?
Would there be more like area for things to diffuse out if you have, or less area, I guess, if you have like really high curvature on that point?
Yeah, but not for small t and when x and y are close. It's kind of surprising. Like essentially what it says is that microscale and macroscale heat diffusion are just very different beasts.
So curvature, you can just make it close enough and like short enough of time.
I mean, this thing, that's right. Like this thing can depend on curvature. It's just that very locally it can. Yeah. Mm-hmm.
Just to clarify, here x and y are like in like R and like the dimension not intrinsic.
They would have to be intrinsic to the surface because the diffusion just doesn't happen outside of the manifold.
What I mean is like x and y some parameterization of the surface, or is it like in like the?
Oh, I see what you're saying. It's in Rn, so like this is embedded in some space. That's right. Yeah, absolutely. because otherwise this distance wouldn't make a whole lot of sense.
Okay, and that's why you need the modulation.
That's right. Well, I think you would need it anyway because you have to account for the distortion of the map. Yeah. These are great questions. I'm glad you guys are thinking critically because this is a funny little formula. Yes?
So in the formula we use in the homework, the guy that begins with a V.
Varidan.
Yeah, Fahrenheit.
Voronoi is a different one. This is Varidan.
So
Yeah.
we made the assumption that t is small. We took the limit as t goes small, but we didn't make the assumption that x and y are close.
That's right. Yeah, in fact, if you made that assumption, it wouldn't be a very useful formula.
So is the geodesic distance kind of like, do we get the geodesic distance when we get rid of that assumption?
That's a really fantastic question, which is like, how do I relate this thing to Varidan formula, right? So remember Varidan formula on your homework and from the previous lecture says what? If I take the log of the heat kernel and I look at small t, then I should get something that looks like distance squared up to the sine. Every time I restate it, I'm stating it in a slightly different way depending on whether I took the log or the square root. But in any event, notice in some sense what this formula is saying is that at least when x and y are close, if I took the log of this object in small t, then somehow, what's the right way to think about it? If x and y are close, then geodesic distance and distance in just the extrinsic space around the surface are not that far apart. That's what this formula is saying, right? Because log of 1 is 0. Yeah. Isn't that sneaky? So yeah, so there's still order in the universe. Like you guys are doing all the right sanity checks, which is fantastic. I'm glad you're thinking critically. All right, any other things that I could? You're keeping me on my toes here. Okay, so this is our handy formula. And essentially what we're going to do here is we're going to say, okay, well, for small enough t, and when x and y are close, which is going to be the case in our point cloud because our point cloud is pretty densely sampled, we're going to be able to make use of this formula. And the trick is going to be that we're going to see a bunch of terms just look like this, evaluated pairwise in our point cloud. And that we're going to kind of use this to justify that our point cloud Laplacian is kind of like taking, solving the heat equation and then taking the limit as t goes to 0 so you get back the Laplace equation. So let's see if we can formalize that a little bit. Okay. Unfortunately now I'm low on space. Is it okay to erase the upper board? 90% of it is just deriving the heat equation. Yes?
Can I ask a bit more about...
You ask away, please.
Can you give some more intuition of what it is? What happens if you have like points that are close extrinsically, but you have like long distance in intricate space?
Close extrinsically and a long distance. So then you would expect the heat equation to decrease, right? So yeah, so I guess for geodesic distances it would likely be a factor less than 1.
All the global structure.
That's right. It's all the global structure just hiding in this psi. Yeah, it's really funny. Notice, by the way, I mean, like, there's so many links between the heat kernel and everything else you might want to do on a manifold. Like, on a surface, as t goes to 0, this number also can be used to measure Gaussian curvature if you normalize the correct way and put in x twice. So somehow, like, going back to your intuition, yeah, then this term had better have something to do with curvature, right? Because that's sort of the only place it can be. Yeah. It's really interesting to think about this little formula, and if you dig in this Belkin and Yogi paper, they have some nice references that show where it's proven by. By the way, there's a textbook. I think it's by Chevelle ? I'm not sure I spelled that properly. Which is basically an entire book on heat kernels, and has all kinds of fun formulas and like. Yeah, it's like one of these books that you should never read, but it's fun to kind of page through and appreciate that somebody wrote it. Don't tell him I said that. Actually, I think he's dead. But I digress. Okay. We're good? We're good. Okay, so now, with these ingredients in place, we can either derive a Laplacian or your instructor will get confused and email you a paper to read later. So let's try. Okay. Right. If only this room contained more than 2 boards. I'm also entertained that they keep telling me that they erased, but they still, the part that you can't see, God forbid you spend the extra 20 seconds. But I digress. Okay. So we need a Laplacian. Right, so let's return to the heat equation. Okay, so what are we going to do? Well, let's think about it this way. Let's say that I have Laplacian of a function u, you know, and u is undergoing heat diffusion, right? So then it's du dt. So if I had some way to diffuse my function out, then I could kind of use that by diffusing a tiny bit and then taking the derivative of that in time, and I get the Laplacian, right? This is like sort of backward. Like if I somehow had access to a way to diffuse, then I could have gotten a Laplace operator. Does that make sense? So this is du dt. So in particular, if I chose some positive t, then what is this thing? Well, be careful. So actually, Laplacian is minus du dt. Sorry. So in particular, we have that it's roughly equal to u of 0 t minus u of x t divided by t for small t. I purposefully swapped the 0 and the t here because remember the heat equation is du dt equals minus Laplace of u. Okay? So here's the really sneaky trick that Belkin and Yogi use. They say, okay, fantastic. I actually know how to do a tiny bit of diffusion because essentially that's what this formula is giving me, right? It's saying that like all I have to do is kind of convolve against this matrix, and that takes my original function u and like spreads it around a tiny, tiny bit on my surface or on my manifold. Yeah? So that gives them a u of x, comma t. We have a u of 0, which is just the original function. You subtract the 2, divide by t, and you get a reasonable Laplace approximation. Okay? Yes?
How do you know psi?
Psi. We don't. But if our point cloud is really, really densely sampled, then psi is roughly just equal to 1. So we're just going to eliminate it. So in particular, here's the approximation they use. They say, okay, what is this thing? Well, we've got this 1 over t factor. That's just this guy. Okay? And then what goes on the inside of this thing? Well, we have u of x0. And just in general, if I wanted u of xt, what do? I convolve u of x0 against the heat kernel, right? So if we plug in our formula for the heat kernel, what are we going to get? We'll get, let's apply this formula here, 4 pi t to the, is it minus? Yeah, minus m over 2. I'm going to run out of space. The integral, you have to be careful, this is over our manifold, which is a little annoying. Yeah. And then if we do our expression here, it's e to the minus mod x minus y squared over 4t, like that, u of y0 dy. This is an approximation. This squiggly equal sign is important. In particular, I've omitted that factor on the right, this psi of x comma y and the big O of t. But for small t, the big O of t term is basically 0. And moreover, here's a kind of interesting thing. If I assume that my point cloud is really densely sampled, so my t is really, really tiny. In fact, actually, never mind point clouds. Let's just say I have really tiny t. Then, like, what is this coefficient when x and y are far apart, basically?
0.
There you go. It's 0, right? Because when x and y are far apart, I'm doing e to the minus big number. Yeah? That's basically 0. And so the argument that they're making intuitively is that the smaller I can get t, that the less and less diffusion I do, the less important that psi term is, because I'm zeroing it out anyway. Do you get that? Isn't that sneaky?
Here's what I found.
T. Most traditional teas do not contain a significant amount of nutrients. Fun fact. Okay, so we're almost there. So this is this formula, and certainly as you take a limit as t goes to 0, this becomes true. Okay. So the only thing that we're missing is we don't know how to integrate. But conveniently for us, integrating on a point cloud, that is actually like a relatively easy thing to do, right? Like, what do? You just sample. I sampled a bunch of points and add stuff up, right? Yes.
The argument that this factor goes to 0 when t goes to 0
Mm-hmm.
doesn't it break down because of the factor in front of it for pt? So that would upscale it again.
That should upscale it again. You're right. There's some argument to make in terms of rate of decrease, but you're safe here. Yeah. I believe big O of t really is the Taylor series big O of t. Like it's linear, this is exponential, and you're good. But I have to think about it. This is an extremely fishy argument because I don't feel like giving you every possible Taylor series term. Okay, so our last task here is just to replace this integral. So what do we say? Well, luckily for us, integrals are roughly equal to sum. So if I have k points in my data set, maybe I just approximate this as e to the minus xi minus xj squared like that over 4t just multiplied by u at point xj like that. So this is just like a sum over your point cloud. Does that make sense? By the way, this is only true up to scale here. So there's some area argument, but that's like not a big deal for Laplacians. Okay, so once I've done all of that, finally, I have an expression that is completely discrete. Do you see that? So I can essentially evaluate this at one of our xi's. So I have the Laplacian at a particular point in my point cloud is given by this funny expression, like 1 over diffusion time times this thing, which again is just u of xi, minus some sum over the point cloud of this basically just Gaussian. Do you see at the end of the day, this whole formula is just saying like, take a Gaussian at every pair of points, multiply it by that matrix, and then subtract off the identity? That's all this formula is. Yes?
What confuses me a bit here is by dropping psi, you completely forgot about the non-Euclidean nature, except for the n in there.
Well, here's the thing. You're right. At long distances, you did. But the Laplacian is a local operator. And so what ends up happening is that you didn't completely forget about the curve structure because you have this distance built in between every pair of points, right? And so like somehow the distances don't add up, like triangularly speaking. A curve in the plane is not a good example because that can be flattened. But think about like a point sampled from a surface in 3D. Like I can bunch them all together by like placing them on a sphere, and now there's like more opportunities for diffusion because these coefficients will be larger. Yeah. It's really, really hard to wrap your head around this stuff. And I think it depends on what order you take your limit. Like you need to take the limit of t, x, and y, all moving, you know, x approaching y and t going to 0 all at a particular rate for this formula to work out. Yeah. Okay, so at the end of the day, we can define a set of weights. And I'll go ahead and give you the set of weights people use in practice because it's slightly different, of course, which is e to the minus xi minus xj squared over 4t if x minus y is less than or equal to some prescribed epsilon. Notice that this is how they get away with basically bounding that psi term. And then there's a question, which is how do you choose this parameter? And that's a very good question and a hard one to answer. And then 0 otherwise. And right, so from this object, it's basically like what? Identity minus this thing is your Laplace approximation. Or a different way of putting it is that this is that the Belkin and Niogi Laplacian operator is the same as the graph Laplacian with edge weights W. So at the end of the day, what do? You just construct a graph on all of your points based on these epsilon neighborhoods. And then using that graph, you use the same graph Laplacian formula we already have. And what comes out is actually a totally reasonable Laplace operator. And basically, the convergence argument that shows that this formula is kind of okay is really just based on this formula that I've stated here. You just have to be really careful with the way you take your limits. Now, the good news is, this is ridiculously easy to code. Do you see that? It's actually much easier to code than what you already did on your homework. It's literally you just take every pair of points and evaluate it in e to the minus stuff. But let's think of all the things that can go wrong. So what are the problems? Well, one is just we do have to be careful about our limit. In particular, you might ask about, like, I'm pointing, but that picture I drew is gone. You might ask about like sampling patterns and like how dense does your sample have to be relative to like what t and so on, right? So in particular, the thing to think about are what are all the parameters that determine our Laplacian formula here. Let's see. If you guys kind of go back to our formula here, like there's some constants that I kind of have to hard code here. What was that? Yeah. One of them is epsilon. This one turns out to matter a little bit less. Like you just end up basically clipping small numbers. But it is true. That is one thing that determines Laplace operator. What's another parameter? T. That's right. Like we have a finite positive diffusion time. Yeah? And here is an annoying bias variance trade-off, right? Because the heat equation gives you the Laplacian as a limit as t goes to 0. Yeah? And this formula is only true in a limit as t goes to 0. On the other hand, what is this double, like what are going to be all the w's if t is really, really close to 0? Basically 0. That's right. And so you need t to be big enough that the points are actually communicating information with one another, but not so large that the heat equation breaks down. Right? This is a very familiar story to Laetitia, who works on a similar topic in her research in a different setting. So in essence, if you look at like t and error of your Laplace approximation, you'll get a curve that looks like that, right? Where here, it's because the heat equation is not the same as Laplacian, right? Like you've diffused for a finite amount of time and not a limit as t goes to 0. And over here, it's because your sampling is not good enough to actually resolve the heat equation at that scale, right? So there's a really tricky matter there.
Does that just mean numerical precision?
It's worse than numerical precision. It's like you have a point cloud, right? Your point cloud looks like this. You really have no data structure for storing heat diffusion that happens in between these points, right? And so somehow that's reflected in the fact that your W's just go to 0. Notice if I had more dense points, I could choose a smaller t and have W's that were meaningful, right? Yeah, it's a tricky matter. But you're also right, like the quadrature of this integral is also inaccurate. There's a lot of problems that go wrong. Okay, so we can see t is a tricky parameter to choose. By the way, in that heat method paper we talked about last time, it's exactly the same issue. There's a third parameter. If we look back at our formula, what have we forgotten to account for? And I think it's because we don't think about it like a parameter when we first kind of present this algorithm, and then we look and say, well, wait a second. Yeah, Tim. That's exactly right. Notice, in this formula, there's this m sitting right here. Yeah? So, as Artem points out, this third parameter, which is m, and what is this thing? So remember I was annoying at the beginning of our lecture, and I asked you to tell me m like it was 1 for a curve? Here's the thing. So let's say I give you the space of photographs that are 128 by 128, and I say I want a Laplace operator on that set of photos. And I say, okay, so what's the dimensionality of that manifold? Any idea? No, well, I don't have an idea either. And so this is where it becomes really problematic. That if you really want this approximation to work out correctly, in every sense of the word, then you need to know the dimension of your data manifold. And there are relatively few settings where that's actually true. So what are we to do? Well, one is you just start guessing. And I would say that is roughly what 90% of people in manifold learning do. I guess the fancy term for this is cross-validation. Laplace operators are fun, but they're a means to some other end, right? You don't just compute Laplacian for Laplacian, you do it to like improve your machine learning model or something. So one thing you can do is say, okay, well, m is the hyperparameter of my model, so I'm gonna like train it with a bunch of different m's and choose the one that performs the best. And maybe, by the way, I learned something about my data set along the way, which is it has some dimensionality here. And there is some give here in this formula. Obviously, there's sort of a continuous dependence on m. In fact, I guess you could take m to be a fraction if you want and like pretend like your data set is some kind of a fractal. I guess. Actually, yeah, you could. Right. But, or you can try to do some reasoning about your data set. There's also some statistical theory out there that tries to give some rules of thumb for how you might guess this thing. Like maybe you look at the sequence of eigenvalues you get from this operator and you choose one that kind of looks the most realistic. But the reality is this is where theory and practice like meet, and there's a lot of open mouth questions here. In fact, there's a broader discussion. People talk about this idea of a manifold hypothesis, like you give me a data set and you say like, does this data set live on some low dimensional manifold and what's its dimension? And answering that in a theoretically rigorous way with like statistical theory and clever kind of backing and a model and so on is really hard to do. To my knowledge, there are very few people that have really nice, rigorous, and practical result in that space. So I think I saw Karthik's hand and then Marcel.
I had two questions. One question is, where does M actually appear in the wave matrix?
I circled it. Oh, in this wave matrix. Oh, you're right. Yeah, I guess, let's see. I guess here, there would be a normalizing constant in front of this thing. My apologies. Yeah. By the way, that does indicate that maybe for this particular Laplace operator, it doesn't matter quite as much as it could. But yeah.
Does this work if the structure of the data isn't actually manifold? Like,
It's a good question. Like, what is this thing?
Or suppose it's
Yeah.
like branches out in this like non-manifold way. Like,
Well, disconnected is fine, right? Because disconnected things still have Laplacians. Branched structures are tricky, right? Because then somehow you have a point where this formula really doesn't make any sense. And by the way, Laplacians don't make sense. Like it's not clear what that would mean. This will give you something, right? I mean, at the end of the day, like if you think about a graph Laplacian, it gives you some notion of smoothness, but it's not clear in the limit what kind of object you get. Yeah. Now Laplacians do exist on like a weirdly large number of structures. So for instance, on a branched manifold, maybe you just like cut out the points that are non-manifold and then evaluate Dirichlet energy. So taking the dual of that will give you a Laplacian almost everywhere, but it won't give it to you at the points that you're asking about. Yeah.
What's
Yeah.
the consequence of getting the number wrong? Like, what if you make it too big or too small?
The consequences are dire. I don't know. Like, what's the consequence of like getting the number of neurons in your neural network wrong? It's a parameter. If you get it wrong, then like your model will be a little worse. But the reality is that like no, I think there is a lot of give here. Like these are, formulas for smoothness at the end of the day. And even if you are slightly off, like you still there's some reasonable notion of like nearby things should have nearby values, and chances are it's okay. Yeah.
If you have a 2D manifold, then that's also a 3D manifold in some sense, right? It's just flat. So
No, go back to your definition of manifold. Remember that the Jacobian has to be non-singular. Yeah. Cool. So anyway, I think the high-level point here is that essentially the Laplace operator for a point cloud is just a pairwise Gaussian plus a little bit of accoutrement around the outside. And at the end of the day, this thing is convergent under some assumptions. There's a whole sequence of papers out there. You could imagine that convergence result for this object is really sneaky because there are many notions of convergence, right? You could ask for a convergence in the number of points being sampled. You could think about it in distribution, like for instance, like if let's say that these points are sampled and moreover they're super dense, but they're not uniformly dense. They're like a little more dense over here than over there. Like you have to ask a question, which is like, does that matter? Do I need to sample my points from Hausdorff measure, or is it okay if like concentration varies a little bit across the domain? This formula suggests that it doesn't, so long as they're super close together. But we're often in the situation where we're not quite so densely sampled, right? Yeah, and you could ask questions about convergence like in eigenvalue. Like I compute this object and then I compute its eigenstructure. You could ask A, is it sensitive to that M parameter? And B, how many points do I need to get a reasonable eigenvalue? These are all fantastic, really hard theoretical questions. Yeah, Artem.
So if you don't have enough points, can't we just upsample point clouds linearly between the neighbors? Like, would it change much nowadays?
Well, there are a number of heuristics you can do to take any point cloud and make it denser, but it doesn't mean that has anything to do with your actual manifold, right? I don't think that that's necessarily any more justified than just using this thing with a bigger T. Yeah.
What's it? I'm just curious, like, what was better to increase the T, and then because there we don't have any like theoretical limits on the.
I don't think you have a theoretical limit on what you're suggesting either, because you'd end up filling parts of space that just you have no information about, right? Yeah, but there are a lot of heuristics you could cook up, and maybe, like for instance, in the universe of data augmentation we have now, maybe you really should think of this object as continuous, because you do have like a little patch sitting around every one of your data points. Doesn't mean that it's a manifold patch, but maybe somehow you can do a little better. Yeah, there's a lot of really good questions to ask here. This is a really fun area and very tangible because the coding is so easy. Yeah. Anything else? Fantastic. Oh, it was, so close. Yes.
No, go ahead.
No, I'm just giving you a hard time.
Do the eigenvectors of this Laplacian give, or like the first few of them, do they give a way to do dimensionality reduction?
Absolutely. Yeah. So the question was like, are the eigenvectors of this thing meaningful? And the answer, I mean, for one, is yes, because this is an approximation of Laplacians, so they have all the same structure we saw before. Moreover, you can use those as an embedding of your data set that has a name. This is called the diffusion embedding of your data set, and is one of the most popular objects to study in applied math. Yep.
It seems like it would be more robust than the methods we studied like a few weeks ago, because like a single bad edge, for example, won't.
That's 100% right. Yeah. So you're right. It's robust. It's if I have some outliers in my data set, the diffusion embedding is unlikely to change quite as much. So it's robust. The only problem is it's not an embedding of the. It's not isometric, right? There's nothing about this construction that says that the eigenvalue should have anything to do with distance on the original domain. And so it is an embedding, but at the same time you destroy the metric. So like if you care about distances, then this is not the way to go, right? Then like MTS makes more sense. If you just want like a nice kind of flat map of your thing that distorts distances a lot, then this can be a better setup. Absolutely. This is popular, especially in medical data analysis. I feel like oftentimes diffusion maps get applied to like low to medium scale data sets. Otherwise, some of these calculations are not super scalable. And so I think you see it a lot there. For instance, at MIT, there's a postdoc in my group, Tal Schnitzer, who you should go talk to, who uses this stuff all the time in her research. Yeah. Okay, so let's go through some interesting applications of this very quickly, and then we'll call it for the day. I'm schwitzing in here. So probably the earliest appearance of Laplace operators in machine learning literature goes all the way back to 2003, although it's really funny because I feel like this idea just keeps coming back in slightly different notation and we don't notice. But the original application was in semi-supervised learning. It was in a paper with a very memorable title here, semi-supervised learning under Gaussian fields and harmonic functions. But we see the word harmonic and we now know like, aha, there's a Laplacian in here somewhere. So here's the basic setting that was considered in the original paper. This was in the dark ages before, you know, like I was in high school. This was a very long time ago. We're given a data set. So for example, this like little helixy looking thing here. And somebody has just labeled a few data points. This is sort of the usual setup. Of course, these days we consider much larger data sets, but their data sets are small. But notice that this is an annoying data set for, in those days, models like the support vector machine, right? Like, there's no plane that like cuts it into the positive and negative samples. Like I can't distinguish those two rings of the helix from one another, yeah? And so there's a procedure that got used a lot in this setting where I've got a very large data set, but most of the data set does not have a label, which is called, aptly enough, label propagation. And here's the basic idea, is I label a few things. So for example, here's this MNIST digits. Somebody's put a graph on them, so maybe like if the pixels are close enough, then I put an edge. And notice like the text here is supposed to signify that like somebody has labeled a few of these with what category they're in. So what are we to do? Well, we want to label on all of the nodes of our graph that are missing a label, and we have it at a few sparse places. That sounds an awful lot like Dirichlet energy, right? We have some function that we want to change kind of slowly across our domain. Yeah? And so here's the formula that was, or the formulation that Jerry Zhu originally proposed. It's very simple. So I put a graph on my data, my unlabeled data. So think about those like helices. And now a few of them are labeled in a binary fashion, and they're going to relax it a little bit. And they're going to allow labels of all the other points to be a number between 0 and 1. Actually, thanks to the maximum principle, we know it won't get bigger than 1 or less than 0. And they do that by optimizing this energy here, where they just say, for every pair of nodes that are connected in this graph, so like think two images are similar, then those images should get similar labels. Does that make sense? And they have a boundary condition, which is that we have the value at a few nodes. So when we optimize this least squares problem, this energy should look very familiar to us by now. This is a Dirichlet energy, right? It's a least squares problem, so at the end of the day, you're going to get a matrix. And what is that matrix? Oh, for God's sake. The Laplacian, thank you. Right, so, you're killing me. Right, so this is their original model for semi-supervised learning. very simple one, and I think actually not all that far off from what a lot of folks do in practice today, which is just we have labels, we have no other information other than just proximity of some data points. Notice that the graph structure matters a lot here, right? Like, so for instance, like this red plus is closer to that blue dot than it is to this labeled blue O over here, but because this graph kind of cuts through this bottleneck here, it receives the blue label. Does that make sense? Cool, so this was the sort of early machine learning approximation or machine learning application of Laplace operators, and it's been proposed and reproposed about 100 times in different places. Here's a related technique. This was proposed by Belkin and Yogi also at about the same time, which is roughly the same. They just do it in the eigenvector space rather than in the original domain. But you can view these algorithms as like roughly the same as each other. In fact, I think they're identical if you compute all the eigenvectors. So this thing eliminates the need to invert a matrix, is essentially what they were after. Okay, interestingly, I mean, the same approach just appears all over the place. In fact, I was just listening to our colleague at IBM give a talk the other day, and once again, so they have a paper on what they call post-processing for individual fairness, and it is precisely this idea once again. So here, let's say that I have a machine learning model that, you know, like I'm trying to evaluate everybody in this room for a loan, and as we all know, like most machine learning models that do this task are like sexist and racist and everything else you can think of, which is extremely problematic. This paper is kind of an interesting one. I would say it's a stepping stone on the path toward fair AI. I would not say that it's the final solution. Hopefully the authors wouldn't disagree with me, where they say like maybe I have a label for every node in my graph. So I have some network where the edges denote that folks are similar under some metric. Like maybe they have similar background or something. And now I have my machine learning model makes a prediction on all these things. And you know, the prediction, you know, now is I can think of it as like I have a graph, and on every node of the graph I have some number or some feature. But that feature, because I have this unfair, terrible AI system, might occasionally give me an outlier. Like, in other words, like this guy's feature might be very different from its neighbors, which I just wouldn't expect because like they're similar people, so they should get similar output. So what these folks propose is very simple. It's just, well, I'm going to have some new feature like f prime. And once again, I'll sum over my graph and say, well, similar people should get similar features, right? But now maybe I have just another one that says, you know, I already have the thing that was predicted by my machine learning model, so now I have some other thing. So the matrix that you get is basically Laplacian plus something down the diagonal, which says like I'm willing to change my features to correct them if my neighbor's features look bad. But in any event, it's kind of interesting to see that basically the same math here gets applied not just for semi-supervised learning, but now in this kind of fairness context as well. Again, I would worry that like, my personal feelings are that like, well, a machine learning model shouldn't go back and try to fix the fairness thing after it's made an unfair decision. So I think there's a larger, you know, I'm supposed to cover ethics in this course, so this is one very small place I can do it. I would say this is an interesting model, and if you're stuck for some reason with the biased AI system, then maybe there's a use case here, but I would encourage you maybe to reconsider the thing that's generating the F-zeros in this setting. But I digress. Okay, one thing to note here. So this semi-supervised learning algorithm that was originally proposed from Zhu and et al. Is actually a very standard thing. This is sort of like a very simple data science tool at this point. You make a graph on your data, you label a few nodes, and then you minimize distribution energy to put label everywhere else. The only problem is it turns out that that's actually ill-posed. So remember we talked a little bit about like when you solve Laplace equation, like Laplace f equals 0, and you just have like point constraints at isolated locations, then essentially the function that you end up computing regresses to the mean very quickly. Meaning that like if I just took the mean value of all the sort of isolated point constraints, most of the vertex labels will be very close to that average. And as I make my point cloud denser and denser approximation of the underlying manifold, it actually gets worse. So these folks actually do the careful math here to kind of tell you why this semi-supervised learning, like if I truly have a graph, it's fine. But if my graph is sampled from a manifold and that's what I'm trying to sort of use as my regularizer, then I have to be so careful when I take the limit, and these folks give kind of different situations where that can be problematic. This is a fun paper to read if you're looking for a good reading assignment this week. There's a reasonable question here, which is how do I fix that? One is to use a higher order operator. So like instead of Laplacian, use the bi-Laplacian or the tri-Laplacian or whatever. If your data is like 50 dimensional though, you need like a 51 dimensional derivative, which maybe is not so great. So there's other ways out of this as well, like maybe puncture your domain or something. But this is where theory and practice meet, and sometimes this manifold learning picture somehow like omits this little detail here, but it's important to remember. That said, if you do omit this picture a bit, this approach has been successfully applied even to regularizing like deep learning models. So in general, back in 2006, but this sort of framework continues to get used a lot. The same basic set of authors, this is unsurprising, continue to study other places where we might use manifold learning, and one of them is what they call manifold regularization. So here, maybe I have a big data set of points that are sampled from my space. So I have like a bunch of photographs that I'm trying to label, and then a few of them actually have labels. This is the usual kind of setting that we have. But now enough of them have labels that I do expect to be able to like do reasonably well in my machine learning tests, but I wonder if I can use the unlabeled data in some way to make it even better, right? This is different from semi-supervised learning case where like you kind of have the whole data set and you're just propagating labels to the missing stuff. So here's what they propose. So here, if we omitted the second term here, notice that this is just our usual machine learning setup. So here I have a bunch of XY pairs, like X is a photo, F is my neural network, and Y is it a cat or a dog? This is the only problem we know how to solve. And now what we're going to do is add a second term to our problem, which is regularizing F. So remember that F is like our neural network. And so the question is like, how can I take my neural network and add some term that says like, maybe I'm pretty sure that this neural network is good or bad using just the unlabeled information that I have. I have this big population of data that doesn't have a label, so I can't include it in term one, but maybe I can do something else with it. Does that make sense? So here's what they propose. They say, aha, well, for a lot of learning tasks, again, I don't expect my label to change all that quickly along my manifold of data, right? So one thing I might do is measure the Dirichlet energy, which conveniently for us is just F transpose point cloud Laplacian F. And notice that this thing does not need Y's, right? This only needs X's. Does this make sense? So it's saying like my machine learning classifier should satisfy two things, right? The first term says it should label my data well. And then the second term says that like if I've got two nearby data points on my data manifold, then I expect them to get nearby labels. Yeah? But notice that in this kind of formulation, if my data set like happened to have, some curve structure like that, that's actually perfectly fine, right? Like, because the Laplacian kind of knows to only propagate information, at least kind of in principle, along the manifold structure. So in this original paper, again, these were the dark ages before deep learning. They show some kind of basic machine learning problems you've probably encountered, regularize these squares and support vector machine. But exactly this framework has since then been applied to deep learning models and modern machine learning. It really doesn't change at all. This is just, another setting. If you read this paper is kind of fun though. Like if you like doing convex optimization, they essentially take that Laplacian term and they show how you can incorporate it into all these classical learning models and optimize it regardless. Then finally, going to, I think it was Karthik's question, but I don't remember. The other paper that's worth reading in this domain is this one on diffusion maps, which does exactly what we suggested, like uses eigenvectors and eigenvalues to embed a data set. Notice that this is very similar to the heat kernel signature and heat kernel map. It's the same formula, it's just applied in high-dimensional stuff. Right? So you're taking some curved data set and mapping it into the spectral space for the Laplacian. And the reason you might do that is it can do things like unwrap these like curved up little structures in your data set. But unlike the methods that we talked about earlier in this course, they don't preserve distances. So they unwrap, but they also squish and squeeze a lot. On the other hand, there are lots of really nice properties. So for example, diffusion maps tend to be very stable to noise and bending and stretching and all that kind of stuff. Finally, I would be remiss if I did not mention that Laplacians lately have had their own little rebirth in the graph convolutional network universe. At this point, this kind of early paper on graph deep learning has been replaced about 70,000 times over. Here, I have some machine learning task on a network. So like, for instance, I don't know, what's my favorite one? I have my social network. I want to classify some of the nodes based on some of the nodes having, labels and other nodes only having some, sparse information attached to them. Or maybe I do some transductive, inductive task, like labeling molecules, something like that. If you look at the typical architectures people use for learning from graphs, they kind of follow, at least the very basic ones, follow what people from my generation would call message passing, right? So in one layer of this network, like I have some belief, for example, of like what I think my label of my node should be, and I can kind of hand it off to my neighbors, using some simple linear algebra and nonlinearity, and we do that a few times. And this is what the sort of original graph neural network structures were doing. And there are a couple kind of funny things. I mean, one thing you might notice is they often call them GCNs, like graph convolutional networks. Of course, convolution is a really fishy term here. There exists no such thing as convolution anymore. But one of the reasons why this is mildly justified is that this message passing thing, if you kind of understand it in the spectral domain from Laplacian perspective, is somehow like messing with Laplacian eigenvalues. And there's an equivalence between that, the same way that like solving the heat equation you can understand as like scaling eigenvalues of Laplacian a particular way. They say, well, if I have the graph Laplacian, I can understand message passing in this sort of spectral domain in a very clean fashion. And so a lot of the theory, at least the early theory, for kind of studying these graph neural networks looks an awful lot like the spectral calculations we've been doing in this course. Of course, these days, now that there are all these specialized architectures, I don't know, we've probably departed from that a bit. If you like this kind of thing, there's this wild and crazy survey, which of course now is a little bit out of date, but is still easy to read, which goes all the way from kind of graph neural networks to learning on surfaces and point clouds and so on. So I encourage you to take a look. If you like this domain, you could easily teach an entire course just in this space. But the good news is you're equipped to read most of these papers. They're quite simple, and the kind of math that they apply really isn't far off from what we're doing here. Yeah?
I'm just curious, what's the convention for authors' names order in the manifold learning?
That is not a question I've gotten in this course before. What is the convention for author named order in manifold learning?
It looks like that's alphabetical.
Well, for one, this is not manifold learning. This is deep learning, and certainly in the machine learning community, I think the convention is usually by seniority, although I'm guessing because these are all grown-ups that this is just alphabetical. Maybe, I don't know. I know Michael Bronstein was sort of the televangelist of this domain, so maybe he was, hard to say. The good news, Archem, we'll step away from deep learning and Laplacians for a minute, is authorship order just doesn't matter. Don't worry about it, guys. Just do good research and get a good recommendation letter from your advisor. In some cases, that person is me. And I guarantee your career will be good. If you're fighting over this stuff, you've done something wrong. That said, in manifold learning, chances are the authorship order would be alphabetical because that community is closer to math. Does it matter? No. The Laplacian is an object that God made, not, But I digress. All right, folks. So with that, we are done with our discussion of Laplace operators. As promised, we've ended early by 2 minutes. And I will catch you on Tuesday. Don't let me forget to post the homework. Somebody already has sent me a reminder. I probably got 5 more during lecture today. It's so weird. You want your homework. But in any event, have a lovely weekend, and I will see you next time.